Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Okay, Lesson 17, Modeling with Polynomials, an Introduction. Classwork opening exercise. In Lesson 16, we created an open-topped box by cutting congruent squares from each corner of a piece of construction paper. Express the dimensions of the box in terms of x. So I used an example that I just made up in the last lesson, but we're going to go with these values here, which is a length of 45.7 and a width of 30.5. So it says to express the dimensions of the box in terms of x. So we're going to get a length. Let me use the right colors. We're going to get a length, which is this distance here. But when we cut the corners out, we're removing an x and an x, which is 2x. So the length is going to be 45.7 minus 2x. The width is 30.5. But again, if we cut here, and they're a distance of x. So if this is x and this is x, and we cut those out and fold the side up, then this distance here is going to be 30.5 minus 2 of those x's, so minus 2x. Okay, and then finally the height is going to equal that x, because if I cut in like this and fold it up, that is our height. So height is going to equal x. So part B says to write a formula for the volume of a box as a function of x. Give the answer in standard form. So as a function of x, and they want volume function of x, we could call it v. Let me use a different color. Let me go to black. So we could say v of x equals, all right, so it's going to be length times width times height. That's the volume of a rectangular prism. So here's the length, here's the width, here's the height. So we're going to multiply all those. So let's just put the x first, and then 45.7 minus 2x times 30.5 minus 2x. Okay, so there is our volume equation with length times width times height substituted in. Okay, since there are fractions or decimals, I am going to use my calculator to help me out here. So remember, when we're multiplying this all out, I would do this first. I would write v of x equals x times, and I'd FOIL this. Okay, so it's going to be 45.7 times 30.5, the first terms. And that is going to give me 1393.85. 1393.85. Okay, plus outer, actually it's not going to be plus. Now we're going to do the outer from FOIL. Outer is the first and the last term. Positive times a negative is negative. 45.7 times 2. 45 times 2 is 90. Plus 7.7 times 2, which is 1.4. So that'd be 91.4x. And then go to the inner, and that's a negative times a positive is negative. And 30.5 times 2 is 61. And then finally, last, negative times a negative is positive. 2 times 2 is 4. X times x is x squared. So then I'm going to just distribute the x throughout, and that is going to give me v of x equals, and I'm going to put this in order from greatest power to least, and I also need to combine my like terms here. So I'm going to do it all at once. So x times 4x squared is going to be 4x to the third. And let me move this over here. See if I have room right here. 4x cubed. So that was x times 4x squared. And then we're going to multiply x times the linear terms added up. Well, 91.4 plus 61.0 is 152.4. So it's going to be minus 152.4, and the x times the x's is going to give us an x squared term. And then finally, the x times the linear is just going to be plus 1393.85x. So there's our polynomial function. 4x cubed minus 152.4x squared plus 1393.85x. Okay, so there's the volume of that rectangular prism. All right, mathematical modeling exercises 1 through 3. The owner of Dizzy Lizzie's, an amusement park, are studying the wait time at their most popular roller coaster. The table below shows the number of people standing in line for the roller coaster T hours after Dizzy Lizzie's opens. Okay, so 0 hours, nobody's in line. Okay, the place just opened. You've got to get through the gate. You got to get to the ride. So at 0 minutes, nobody's there. After 1 hour, or 0 hours, I guess. So at opening, no one's there. At 1 hour, there are 75 people in line, and so on and so on. And after 12 hours, it tapers back down to 45. We're getting near the end of the day. People got tired. Kids get tired, and they go home. Jalen made a scatter plot and decided that the cubic function should be used to model the data. His scatter plot and curve are shown below. Okay, so there's the setup of the problem. Okay, page 2. Number 1, do you agree that a cubic polynomial function is a good model for this data? So when I look at this data, here is the line of the cubic. So it came down here. You just don't see the minimum here, and it turned and went back up. These points are on or pretty close to that set of data. So I would say yes, the curve passes through most of those points, and it seems to fit the data. And that's what I would say. Okay, so there it is. And number 2, what information would Dizzy Lizzie's be interested in learning about from this graph? How could they determine that answer? Okay, so in response to that, you could say the company should be interested in the time when the line is the longest and how many people are in line at that time. To find this out, they can find a model that could be used to predict the number of people in line at any time during the day. They could then estimate the maximum point from the graph. Number 3 says to estimate the time at which the line is the longest and explain how you know. Okay, so without taking this into consideration, because it's beyond our hours, after 12 hours, okay, the reason it's going back down to 0 here, so there's nobody in line here. They can't have negative people in line and then have positive again. So we're really just concerned with the values between here and what's that, 13 hours? That's probably their hours of operation. Okay, so estimate the time at which the line is the longest. That's when there's the most people in line. Well, that is going to be right there. So when I put a dot there and I come down here, here's 5 right here. This is 5 hours. And this is 6. 7, 8, 9, 10. These are 1 hour increments, and this falls halfway in between. So I would estimate it'd be approximately 5 1/2 hours. There is the longest line. How do you know? That is where the graph reaches its maximum. Okay. Number 4, estimate the number of people in line at that time. Well, to estimate the number of people in line at that time, let me get a line here and make it thin. And let's make it green. So if I choose that point right there and I come over and make a straight line over to the side there, that is my f of x or my y value. And that is occurring at 250, 375, 1, 2, 3, 4, 5. It took 5 squares to get from 250 to 375. So 5 That's a difference of 125. So I want to know how many each square is. So 5 times 2 is 10, and you get 25. So it's 25 times 5 is 125. So this is 250, 275, 300, 325, 350, 375. So it's a little more than 350, but it's less than 375. So I'd guesstimate that it'd be about 365 or so. All right, so I would say approximately 365 people. Okay, it does say to estimate, and that's would be my estimate. Now, what we could do is take the value of our function, and I'm going to do that now just to show you. Remember, we did get an f of x from this. Let me set this up, turn off my plot from my last problem. So if I go back, we came up with this, well, that was the volume of the box, never mind. We didn't come up with an equation for this yet. But if we looked at 5.5 hours, we know we're in between these two values, okay? So I guess I didn't need to go back a page, it's right here. So 5.5 is between 4 and 7. We know it's between 345 and 355. And let's see, 5, 6, 7. So it should be higher than that. So it's continuing to go up above these because it's above this. The middle is more than at my point at 7 hours. We are higher. Okay, so I will stay with that approximate 365 people. Okay, now number 5 says to estimate the t-intercepts of the function used to model this data. Now, when they say t-intercepts, our x-axis is our t-axis and our y-axis is our p. So the number of people in line at any given time is what that means. So it says to estimate the t-intercept of the function used to model this data. Okay. So what they're saying is, where is this function crossing? So I want to know what this value is here, this value here, and this time here. So let me scroll up. So I would say t equals 0. Okay, right here at 0 hours, it was 0. And then I look back up at my graph here, and it's got to be after 12. We're tapering down. So after 12, so here's 10, here's 11, here's 12. I'd say it would be a little bit more than 12. So let's just say 12 and a half or 12.5. At time 12 and a half hours, we're back to 0. And then back up to 0 at time t equals, and this is 30, 1, 2, 3. It looks like about 33. So it says use the t-intercepts to write a formula for the function of the number of people in line F after t hours. So now we're going to use our zeros, and let's get rid of that fraction. We don't ever use fractions in our function. So how would we do that? Well, if t equals 0, then if t equals 0, then t is a factor. If t equals 12.5, then t minus 12.5 is a factor. If t equals 33, then t minus 33 is a factor. Okay, so we're going to use those 3 values. So what are we trying to find? A function with respect to t. So let's just call it f of t. So f of t equals t times t minus 12.5 times t minus 33. Okay, where c is a constant that has not yet been determined. So there it is. That's number 6. Okay, so with my equation here, I have assumed that this is 0. It may not be 0. It might be 1. It might be 2. It might be something really close to 0. It can't be negative, of course. So with that in mind, I'm going to use a different color. I'm going to say that this is c times t right here. Okay, so if you have some constant we haven't figured out yet, that should be c times t. So then when we find the constant, then that can be figured in. Okay, so let's just call that CT for now, a multiple of the time and the constant. So use the relative maximum to find the leading coefficient of f. So I use this relative maximum here of 365. So what I'm going to do is use that value, and that is f of 5.5. So I'm going to say f of 5.5 equals 365. That's what I'm going to start with. So we can plug in 5.5 into this function above right here and find that. So let's do that. So if I take f of 5.5, that is going to equal c times t. Actually, let me multiply that c through. Okay, so if f of 5.5 equals this function right here, and we don't know the constant, we're going to write c, and then we're going to substitute in 5.5 for all of these t's. So it's going to be c times 5.5 times 5.5 minus 12.5 times 5.5 minus 33. So all I did was put 5.5 here, here, and here, because t is 5.5, f of 5.5. And we know it equals approximately 365. That was my approximation. And so now we're going to finish this by simplifying. So f of 5.5 is going to equal 5.5c times, and 5.5 minus 12.5 is negative 7. And 5.5 minus 33 is negative 27.5. So then when I take 5.5 and multiply all these values out, I'm going to get 5.5 parentheses negative 7 parentheses parentheses negative 27.5. And I get 1058.75. C. But I know f of 5.5 is 365, so I'm going to replace that now with 365 equals 1058.75. And then what that's going to produce is my c when I divide both sides by that. So I'll get my calculator and take 365 divided by the answer I just had. And that is going to give me 0.34 approximately. So that's an approximation. And it's going to be 0.34. That's pretty messy. All right, an approximation of 0.34. There is my constant. So then I would come back to this function and put, instead of the c right there, put plus 0.34 when I just multiplied this all out. What would be a reasonable domain for your function f and y? Well, the domain is the number of, what is the domain? Domain is time. So a reasonable domain would obviously be t being between two values, obviously. And we can't have negative time. So that when the doors open, when the gates open, that is times 0. And depending on how long the park is open, the amusement park's open, looking at this, it appears to be about 12.5 hours. So my domain would be the set of all values time between 0 and 12.5 hours. Okay, and I misspoke here. Looking back at this, it says using relative maximum to find the leading coefficient of f. This is the leading coefficient. So that would be 0.34t. times t minus that times t minus that. All right, leading coefficient of 0.34. Okay, page 3. Use your function f to calculate the number of people in line 10 hours after the park opened. So remember my c was 0.34, so my f of t is now, I'm going to use this function with 3.4 in for c. So I would say f of 10 equals 0.34 times 10 times 10 minus 12.5 times 10 minus 33. So f of 10 is going to equal 3.4 times negative 2.5 times negative 23. So my f of 10 is going to equal 3.4 times negative 2.5 times negative 23. And my answer is 195.5. Okay. So obviously we can't have a half a person. So you would say approximately 196 people would be in line 10 hours after the park opened. Okay. 10 says to compare the value calculated above to the actual value in the table. Is your function f an accurate model of the data? So I'm going to go back and look at 10. Is it near 196? So I go back and I look at 10 and it's 180. So we're off by 16. So 180 was in the table and my approximation was 196, which is a difference of 16 people. And it's less than 10%. So I would say, yeah, that's okay. We're within 10% of the actual. So that would be a good value. Okay, now it says use the regression feature of a graphing calculator to find the cubic function g to model the data. All right, so I'm going to go back a page. We're going to put this data, let me move that out of the way. This is going into our calculator, so let's review that. I always clear my home screen. I always go to y equals, clear that, arrow up to plot 1 and turn it on because we're plotting statistical data. And then we press the stat button. We hit edit to enter our data. To clear something that's already there, you arrow up to L2 and hit clear, arrow down, it goes bye-bye. Do the same in L1, clear, down, bye-bye. All right, so X is your L1, or T in this case is your L1. So I enter 0, enter 1, 2, 4. I'm entering the data in this table, by the way. 7, 8, 10, 12. Okay, so if I go back up to the last number, this for 8 in parentheses tells me there are 8 pieces of data in my L1. 1, 2, 3, 4, 5, 6, 7, 8. Always make sure that's correct. Then we put in our Y's, in this case, P, people. So 0 is going to be 0, then 75, 225, 345, we do not want to be at the end of that line, 355, 310, 180, and finally 45. Okay. Go back to your last entry, make sure that's an 8. These cannot differ. You'll get an error and it will say error mismatch because you don't have the same number of X's as you do Y's, and that can't calculate anything when that happens. So there is my data. Then I'm going to go to my home screen. I'm going to press stat, calculate, And what regression did they ask for? Use a regression feature to find the cubic function. So we're going to do a cubic regression, which is 6. So let me start that over. Clear, stat, arrow over to calculate. We want a cubic regression, which is 6. We want L1 and L2 to be our X and Y, and you just hit enter until it says to calculate. And there are our values. So this is the best way to get your data. It's right on this page. So I'm going to write that now. Use the regression feature. So A is 0.37. So it's going to be f of t equals 0.37 x cubed. B is negative 16.6 minus 16.6. Alrighty. Minus 16.6 x squared. My c is 150. C is the linear coefficient. That's going to be plus 150.3 x. Okay. And then finally, d is minus 21.25 or minus 21.3. I just rounded them all to the 10th. So use the regression feature of the graphing calculator to find the cubic function to the model of data. So there it is. Now I could also graph this. If I go into y equals now, if I press vars, 5 for statistics, arrow over to EQ and put that regression equation in y1. And then if I hit zoom statistics, which is zoom 9, then it will show my data that I plugged in from the table, and it will show that function that we just calculated, which is written here in green. And it looks like a really good fit. So 12 says graph the function f you found and the function g produced by the graphing calculator. Use the graphing calculator to complete the table. So I need to change something here. They wanted us to call the one we used in the calculator g of t, not f of t. Okay, that's the regression equation. Okay, so f of t, your equation. So what I'm going to do now, just to save time, I'm going to go to y equals, where was my equation? Right here. I never put it into standard form, but I will just write it out like this. It is going to be 0.34 x parentheses x minus 12.5 and x minus 33. Okay, and I'm going to graph that. So there is the graph f of t. And now I'm going to graph this one by doing stat calculate 5. Okay, that, and then go to y equals vars 5 EQ, enter. Graph. Okay, so see how close they are? They're close. One is just under, and then they cross over, and then it's over, and then it crosses again. They're back under, but they're both pretty close. All right. So if I go back to y equals, and I want to enter my f of t values, then I'm going to turn off this one to eliminate confusion, and I hit second graph, and now I'm going to enter those values for x. 0 gave me 0. This is my f of t. And then 1. Okay, and I'm just going to enter these all right now first. 2, 4, 7, 8, 10, and 12. Actually, let me wait on that and enter these first because it will replace my 10. So 0, 0 I have. 1, let's just round it even. 125 people. You can't have parts of people. Then it's 221 for 2. And then 4 gave me 335 people in line 4 hours after. 7 hours after was 340. 8 hours after gave me 306 people. Oop, timer's off. Stop. Okay. 10, 196. And finally 12. Now I'll hit enter, and that is 42.8 or 43. Okay. And now I'm going to go back to y equals. I'm going to turn that off by turning off that equal sign. Arrow down, turn that equal sign on. Hit second table. And now the values all change for my new value. So 0 is now 0.12 people. So I'm just going to call that 0. And 1 is 109. 2 is 198. 4 is 318. 7 is 352. 8 became 325. 10 isn't there, or I'll have to enter it. 20 is 20.6, or say 21. And then I just need to enter 10 over here. So I'm going to put 1, 0, enter, and that gave me 211.7. Let's call that 212. Okay, so there are our values. And really close, 125, 109, it's off a bit. This one's higher than this. This one's an overestimate to the regression. This one's over, this one's under, this one's under, and then this one's under, and then it went back to over, as the graph showed. Based on the results from this table, which model is more accurate at t equals 2 hours? So here it is. Which one is closer? The one that was closer at t equals 2 hours, f of t at 2 hours was closer. At t equals 10 hours is right here. The answer was 180. F of t was 196. The regression was 212. Again, f of t was closer at 10 hours. Okay, page 4 brings us to the end of lesson 17. Go to your problem set.